The night sky has always surprised us with visitors from beyond our solar system. In recent years, astronomers have discovered objects traveling so fast on paths so strange that they cannot possibly have come from within our own celestial neighborhood. The third such object, named 3I/ATLAS, raises a question both thrilling and unsettling. Is it just another comet, or something far more extraordinary? Chapter 1. The Unexpected Visitor. In April 2019, astronomers operating the Asteroid Terrestrial Impact Last Alert System, or ATLAS, in Hawaii, detected a faint moving dot against the backdrop of the stars. ATLAS was designed to scan the skies for near-Earth objects that could pose a threat to our planet. But instead of finding another asteroid, it had stumbled upon something far stranger. The object, later named 3I/ATLAS, was not bound by the gravity of our solar system. The 3I designation tells an important story. The I stands for interstellar, and the 3 indicates that it was the third interstellar object ever detected, after the famous Oumuamua in 2017 and Comet Borisov in 2019. Unlike most comets and asteroids, which orbit the Sun in predictable paths, interstellar objects are just passing through, cutting across the solar system on hyperbolic trajectories. From the very first orbital calculations, scientists knew this was not an ordinary comet. Its trajectory, speed, and origin direction suggested that it was a true wanderer from another star system, traveling for millions, maybe billions of years before entering ours. But what exactly was it, and how could we tell? That's where the mystery deepens. If it behaved like Borisov, with a clear cometary tail and active outgassing, perhaps it could be explained. But if it acted more like Oumuamua, with unusual acceleration and a puzzling shape, it might spark new debates about whether nature was the only possible explanation. So what did 3I/ATLAS show us? To answer that, we need to take a step back and look at the history of these rare cosmic visitors. Chapter 2. Oumuamua and Borisov. The predecessors. Before 2017, astronomers had suspected for decades that interstellar objects should exist. Stars are constantly forming, interacting, and scattering debris. Theoretical models suggested that during the early formation of planetary systems, trillions of objects would be ejected into interstellar space. It was only a matter of time before one of them wandered close enough for us to notice. That first confirmed detection came in October 2017, when the Pan-STARRS telescope in Hawaii spotted a strange object moving far too fast to be from our solar system. Named Oumuamua, Hawaiian for scout, it quickly became one of the most debated objects in astronomy. Its elongated, cigar-like, or perhaps pancake-like shape, combined with its unexplained acceleration as it left the Sun, made it unlike any comet or asteroid we had ever seen. Some researchers even suggested, cautiously, that it might be artificial, a possibility that stirred headlines worldwide. Just 2 years later, in 2019, Comet 2I Borisov entered our skies. Discovered by amateur astronomer Gennady Borisov, this interstellar visitor looked and behaved much more like a normal comet. It had a bright coma, a long tail, and clear signs of volatile gases evaporating as it approached the Sun. For many scientists, Borisov confirmed the expectation that interstellar comets should exist in great numbers. But it also raised a puzzle. Why had the first one we found, Oumuamua, been so unusual? Was it simply an outlier, or were we missing something deeper about the diversity of objects roaming between the stars? When 3I/ATLAS appeared, the hope was that it might help settle this debate. Would it look like Borisov, easing astronomers' minds, or would it behave more like Oumuamua, reigniting the possibility that we had seen something extraordinary. Chapter 3: A Faint and Fragile Comet. At first, 3I/ATLAS seemed to follow the cometary script. Its discovery images showed a diffuse halo of material around it, suggesting outgassing. That was a relief to many astronomers. It looked like another Borisov, another piece of icy debris knocked free from a distant star system. But as weeks passed, the story changed. Astronomers tracking 3I/ATLAS noticed that it was fragile, breaking apart under the stress of solar heating. By May 2020, it had fragmented into multiple pieces, effectively destroying itself before it could make its closest approach to Earth. This fragmentation was both frustrating and fascinating. On one hand, it meant we couldn't get as clear a picture of the object as we had hoped. On the other, it told us something critical. Interstellar comets might be extremely delicate, more prone to breaking apart than many comets we know from our own solar system. Why would that be? One hypothesis is that interstellar comets spend eons in the cold emptiness between stars, where cosmic rays slowly weaken their structures. Another possibility is that 3I/ATLAS had an unusual composition, rich in volatile ices that made it unstable when exposed to sunlight. If that's the case, then perhaps Borisov was the rare exception, a comet sturdy enough to survive its passage intact. But the deeper question remained: what does this fragility tell us about how these objects form and where they come from? Chapter 4: The Journey Between the Stars. To understand an object like 3I/ATLAS, we need to imagine its journey. Picture a planet-forming disk around a young star billions of years ago. Countless icy bodies form on the outskirts, some stable, others unstable. As massive planets form, their gravity acts like a slingshot, scattering many of these icy leftovers into deep space. Most will wander the galaxy forever, never approaching another star. But a tiny fraction will, by chance, pass through systems like ours. That's what makes 3I/ATLAS so rare. It had to be ejected from its birthplace, survive countless millions of years in the void, and just happen to cross Earth's neighborhood at the right time for us to see it. What's astonishing is that these detections may only be the tip of the iceberg. Estimates suggest there could be trillions of interstellar comets drifting through the galaxy at any moment. The fact that we have already found 3 in just a few years suggests they are more common, and perhaps more important, than we once thought. But here's the cliffhanger. If billions of these objects are passing through, how many go unnoticed? And what secrets could they carry about the birthplaces of alien worlds? Chapter 5: What the Spectra Reveal. When astronomers study comets, one of their most powerful tools is spectroscopy. By splitting the light reflected or emitted from a comet into its component colors, scientists can determine its chemical makeup. For 3I/ATLAS, telescopes around the world raced to collect spectra before the object broke apart. The data showed familiar features: water vapor, carbon monoxide, and other volatiles common in comets from our own solar system. In that sense, 3I/ATLAS looked natural. It wasn't composed of exotic materials or strange compounds. It was made of the same stuff that makes up our icy bodies. This was both reassuring and tantalizing. It suggested that the processes forming comets in other systems are similar to those here. In other words, planetary formation might be universal, producing similar ingredients everywhere. That has huge implications for understanding the origins of planets, and even life. But spectroscopy can only tell us so much. We couldn't recover solid fragments of 3I/ATLAS. We couldn't send a probe to fly by. And because it disintegrated so quickly, The window of observation was painfully short. Did we miss something critical? Could there have been unusual isotopes or rare compounds hidden in the debris cloud? That's where the frustration lies. Each of these interstellar visitors gives us just a glimpse, and then they are gone forever. Chapter 6. The Alien Probe. Hypothesis. Every time a strange interstellar object appears, the question inevitably arises, could it be artificial? With Oumuamua, this idea caught fire because of its unexplained acceleration and odd shape. Avi Loeb, a Harvard astronomer, famously suggested that it might be a probe sent by another civilization, perhaps a thin solar sail designed to use starlight for propulsion. Most scientists disagreed, preferring natural explanations, but the debate highlighted how little we really know. With 3I/ATLAS, the case for artificial origin was far weaker. It looked and behaved more like a comet, and its disintegration fit well within natural models. Still, some wondered, if we were to encounter alien probes, might they sometimes disguise themselves as natural objects? Could fragile, fragmenting comets serve as camouflage for something more? That idea remains firmly in the realm of speculation. There is no evidence that 3I/ATLAS was artificial, but the very fact that we must ask the question reveals how these interstellar visitors stretch our imagination. And it raises a bigger question. If 3I/ATLAS was just another comet, what would it take for us to recognize something truly artificial? Would we know it if we saw it? Chapter 7. Lessons from a Broken Comet. The breakup of 3I/ATLAS might seem like a disappointment. After all, a comet that falls apart leaves us with little more than a cloud of dust and gas. But in astronomy, even destruction can be revealing. As 3I/ATLAS disintegrated, telescopes captured the fragments spreading out along its orbital path. By measuring how quickly the pieces drifted apart, astronomers could estimate the strength of the comet's nucleus. The results were striking. 3I/ATLAS was far weaker than most comets we've studied in our solar system. Its nucleus may have been held together only loosely, like a cosmic snowball barely bound by its own gravity. That fragility might explain why interstellar comets are so rare in our observations. If most of them break apart before reaching the inner solar system, only the toughest survive long enough for us to notice. 3I/Atlas may have been one of countless fragile wanderers that never make it intact. But here's the puzzle. If interstellar space is filled with fragile, short-lived comets, what does that mean for our ability to study them? Are we only ever going to glimpse them as they die? Or could future technology allow us to intercept them before they fall apart? That question leads us to one of the most exciting frontiers in astronomy. Missions designed not just to observe interstellar objects from afar, but to chase them down directly. Chapter 8. The Race to Intercept. The discovery of Oumuamua and Borisov sparked a bold idea in the scientific community. What if we could send a spacecraft to an interstellar object while it's still passing through? The European Space Agency has already proposed such a mission, known as Comet Interceptor. The plan is to build a spacecraft that waits in space until the next interstellar visitor appears. Then, using stored fuel and a clever trajectory, it would launch itself on an intercept course, flying by the object to take close-up images and measure its composition directly. For 3I/ATLAS, such a mission would have been invaluable. Imagine being able to capture detailed images of its nucleus before it fragmented, or to directly sample the gases streaming from its surface. We could have compared its chemistry to that of comets from our own solar system and asked, Do all planetary systems build comets in the same way? But the challenges are immense. Interstellar objects move incredibly fast, often tens of kilometers per second. By the time we detect them, they are already racing through the solar system, leaving us only months or even weeks to respond. That's far shorter than the years of planning usually required for deep space missions. Still, the potential is too great to ignore. Each of these objects carries with it the fingerprints of another star system, frozen in ice and rock. If we could study even one up close, it might transform our understanding of planetary formation across the galaxy. But until then, we are left with only telescopes and theories, and those theories raise even deeper questions. Chapter 9. What do interstellar comets tell us about life? One of the biggest mysteries in science is the origin of life. Did it arise uniquely here on Earth, or is it common across the universe? To answer that, we need to understand how the building blocks of life, molecules like water, carbon compounds, and organic chemistry, are distributed in space. Comets are critical to this question. In our own solar system, comets are thought to have delivered water and organic molecules to the early Earth, seeding the conditions for life to emerge. If comets in other star systems have similar compositions, it suggests that the ingredients for life are widespread. The spectra from 3I/ATLAS revealed familiar molecules: water, carbon monoxide, and perhaps traces of other volatiles. That means that across light years of space, other star systems are building comets much like ours. And if those comets can carry the seeds of life, then life itself may not be rare. Here's the tantalizing thought. Interstellar comets don't just passively wander the galaxy. They may actively transfer material between star systems. In a process called panspermia, microbes or prebiotic molecules might hitch a ride inside comets, protected by ice, surviving journeys lasting millions of years. Could 3I/ATLAS have carried the building blocks of alien life? We'll never know for sure, but its chemistry suggests the possibility cannot be dismissed. And if that's true, then every interstellar comet we detect might not just be a piece of rock and ice, it might be a messenger of life itself. Chapter 10. A window into other worlds. The beauty of interstellar visitors like 3I/ATLAS is that they offer a rare window into places we may never reach. Each comet or asteroid ejected from a distant star system carries with it a sample of that system's history. Imagine, for a moment, trying to understand a faraway civilization by the artifacts that wash up on your shores. Each object tells a story of where it came from, how it was made, and what forces shaped it. Interstellar comets are like those artifacts, drifting into our solar system to give us a fleeting glimpse of alien worlds. With 3I/ATLAS, the glimpse was brief and incomplete. It broke apart before we could learn everything we wanted. But even in its destruction, it told us something profound, that comets from other stars are not so different from our own. Planetary systems across the galaxy may be building the same icy wanderers, scattering them into the void, and sometimes sending them our way. But if they are so similar, why was Oumuamua so strange? Why did the first one we ever detected defy our expectations so completely, while the next two looked more like familiar comets? Is it possible that interstellar space holds not just icy wanderers, but entire categories of objects we've never imagined? That question leads us to the next mystery. What lies ahead in our search for more interstellar visitors? Chapter 11. The future of interstellar exploration. Astronomers are confident that 3I/ATLAS will not be the last interstellar object we encounter. In fact, with new telescopes coming online, we may soon detect dozens or even hundreds every year. The Vera Rubin. Observatory in Chile, scheduled to begin its full survey soon, will scan the entire sky with unprecedented depth and frequency. It is expected to revolutionize our ability to detect faint, fast-moving objects, like interstellar comets. Within its first decade, it may discover dozens of Oumuamua-like visitors, giving us a much clearer picture of how common they really are. Each new discovery will add pieces to the puzzle. Some may look like Borisov, ordinary comets from other stars. Some may resemble 3I/ATLAS, fragile and short-lived. And perhaps, just perhaps, one will challenge us again, behaving in ways we cannot explain. If that happens, will we be ready to recognize the extraordinary? Or will we, as with Oumuamua, be left debating natural versus artificial explanations long after the object has vanished? Chapter 12. The Endless Mystery. 3I/ATLAS may not have been as dramatic as Oumuamua or as photogenic as Borisov, but it holds an important place in the story of interstellar exploration. It was the comet that reminded us how fragile these visitors can be, how short our window of opportunity is, and how much we still have to learn. It confirmed that comets from other stars can resemble those in our own system, suggesting a universality to the way planets and small bodies form. And it hinted that the ingredients for life may not be confined to one star, but scattered across the galaxy. Was 3I/ATLAS an alien probe? Almost certainly not. The evidence points to a natural origin. But in some ways, the truth is just as profound. Because even as a fragile, broken comet, it was a messenger from another star system, carrying secrets of a distant world across unimaginable distances, only to fall apart under our sun's heat. And that leaves us with the ultimate cliffhanger. The next time a visitor arrives, and there will be a next time, will we finally be ready to catch it before it vanishes forever?